Period, frequency, and speed of a longitudinal wave. Physical Sciences, Grade 10. At the end of this lesson, you will be able to calculate the period using the expression period T equals to 1 divided by the frequency f. Calculate the frequency f using the expression frequency f equals to 1 divided by period T. Use the wave equation, which is that the speed v equals the frequency f multiplied by the wavelength lambda, to perform calculations related to longitudinal waves, and use the expression for speed, which is the speed v equals to the distance x divided by the time taken, to perform calculations related to longitudinal waves. A longitudinal wave has a compression to compression distance of 15 meters. It takes the wave 7.5 seconds to pass a point. The first thing we can do is to draw a diagram of a longitudinal wave. A longitudinal wave is made of regions where the particles are closest, such as here, 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 and here. And these regions are called compressions. A longitudinal wave is also made of regions where the particles are a bit far away from each other, such as here, here, here. And these regions are called rarefactions. We are told that the compression to compression distance is 10 meters or is 15 meters, right? This means that the distance from the start of one compression to the start of another compression or the following compression is 15 meters, right? We can label the point from the start of the first compression and call it A, and the point from the start of the second compression and call that B. This means that the distance from A to B is 15 meters. So now question A says, determine the wavelength of this longitudinal wave, given all this information. We are not given the wavelength, but we have just said that the distance from A to B is 15 meters. Points A and B are said to be in phase. If 2 points are in phase, or if 2 points appear at the same position when the wave repeats itself, such as A and B, they are said to be in phase. More scientifically, we say points A and B are in phase because they are separated by a full or complete wavelength. The distance for one complete compression and one complete refraction is one wavelength. So if you look at that from A to B, so you have a complete compression where the particles are close together and a complete rarefaction where the particles are a bit far apart from each other. Therefore, the distance from A to B is also a wavelength. I hope that is clear. Now, if A to B equals to 15 meters and A to B also equals to the lambda or wavelength lambda, this means that the lambda or the wavelength is equals to 15 meters. It's the same distance, right? So we can just say that the wavelength of this longitudinal wave is simply 15 meters. Let's look at question B of the same question. Calculate the speed of this wave. There are two ways to solve this problem. The first way is to use the wave equation, which is the speed v of the wave equals to the frequency f multiplied by the wavelength lambda. The speed v must be in meters per second, the frequency must be in hertz, and the wavelength lambda must be in meters. We know that the wavelength lambda is equals to 15 meters as we determined in question A. Now to calculate the frequency f, we need to know the period t. The question provides us with the time it takes a wave to pass a point, and this is the period t, which is 7.5 seconds. The period t is the time it takes a complete wave to pass a fixed point. We know the wavelength lambda, which is 15 meters. We also know the period t, which is 7.5 seconds. What we don't know is the frequency f, which must be measured in hertz, but from the period t, we can determine the frequency. There's a relationship between the period and the frequency, and I'll show you just now. And when we have the wavelength as well as the period, we will be in a position to determine the speed of this longitudinal wave, which must be measured in meters per second, right? So to solve, to find the speed, we use the wave equation, which is that the speed v equals to the frequency f multiplied by the wavelength lambda. But we also know that the frequency is related to the period through this equation here, which is 1 divided by t. So we can just substitute in the place of f, we can just substitute 1 over t. And when we do that, we are left with the speed v equals to brackets 1 over t multiplied by the wavelength lambda. And then if you multiply the wavelength on the right hand side, you multiply 1 multiplied by lambda is just lambda all divided by t, so that you are left with that v, or the speed v, equals to the wavelength lambda divided by t, right? And from here, it's just a matter of substituting the known values of the wavelength, which is 15 meters, all divided by the known value of the period, which is 7.5 seconds. And if you do that calculation, you will find that 15 divided by 7.5 equals to 2 meters per second. Therefore, the speed of this longitudinal wave is 2 meters per second. Another way to calculate the wave speed is to use the expression the speed v equals to the distance x divided by the time taken t, where v is measured in meters per second, x, the distance, is measured in meters, and t, the time, is measured in seconds. So we know that the distance x from A to B is 15 meters. That is the compression to compression distance that was provided to us in the beginning. And the time taken is t, which is 7.5 seconds. So if we are given those values, we are given the distance x, which is equals to 15 meters, we are given the time taken, which is equals to 7.5 seconds, we then need to determine or to calculate the speed v, and that must be calculated in meters per second. So we will solve using the expression v equals to, or the speed v equals to the distance x divided by the time t. And from here, it's just a matter of substituting the known values of the distance, which is 15 meters, divided by the known value of the time, which is 7.5 seconds, and If you do that, you have that V equals to 15 divided by 7.5, which will give us 2 meters per second. Therefore, the speed of the wave equals to 2 meters per second. A flute produces a musical sound traveling at a speed of 320 meters per second. The frequency of the note is 256 Hz. Imagine Lizzo playing a flute. A flute produces sound using wind. Now, the wind that Lizzo blows into the instrument shakes or vibrates the air particles inside it. This is what makes the sound. Sound comes from vibrations, and sound is a longitudinal wave. On the next video, or in the next couple of lessons, we will talk about sound as a longitudinal wave. As they are blowing through the flute and sound is created, it is said that the sound wave travels at a speed of 320 meters per second, and that the frequency of the note that is played is 256 Hz. So question A requires us to calculate the period. We are given that the frequency is, or the frequency F is 256 Hz, and we have to find the period T, and that must be in seconds. To solve this, we use the expression that T, or the period T, equals to 1 divided by the frequency F, whereby when you have done this, it's just a matter of substituting the known value of frequency. So you have that the period T equals to 1 divided by the frequency, which is 256 Hz. And if you calculate that, you'll find that it gives us the value of 0.0039 seconds. This means that the period T of the wave is 0.0039 seconds. Question B. Calculate the wavelength. So we are given that the speed V of that sound was 320 meters per second. The frequency was given to us as 256 Hz, and we must find the wavelength, and that wavelength must be in meters, right? And we will solve this problem by using the expression of the wave equation, which says that the speed V equals to the frequency F multiplied by the wavelength lambda. Now, to do this, we must first make the wavelength the subject of the formula, or we must make lambda the subject of that formula. How do we do that? We do that by dividing both the left-hand side and the right-hand side of the equation by F. So on the right-hand side of the equation, you have F times lambda divided by F, and on the left-hand side, we have that the speed V divided by F. So you know that F, so if you look at the right-hand side, F divided by F is 1, and 1 multiplied by lambda is just lambda. This means that on the right-hand side, you will only be left with lambda. And then on the left-hand side, you'll be left with the speed V divided by the frequency. So we know that the wavelength lambda is given by the speed V divided by the frequency F. And we now just substitute the known values for the speed V, which was 320, divided by the known value of the frequency, which was 256. And 320 divided by 256 equals to 1.25 meters. This means lambda equals to 1.25 meters. This tells us that the wavelength of the node that was played by that flute is 1.25 meters. This might have felt like a lot. However, if you keep practicing, it will become easier and easier to understand. The trick is to keep practicing and doing more and more challenging problem sets. We have seen how we can calculate the period t, the frequency f, and the speed v of a longitudinal wave. I have said that sound is a form or is a longitudinal wave, and in the next video I will explain just why.